What happens when a machine starts discovering math that humans could not crack for centuries? That's the question we are going to live with tonight. But before we get to the shiny world of AI, and before we get to computers crunching numbers while we humans are just sitting there eating chips, we need to go way back to when math was not something that lived in textbooks, but something that haunted human beings like a bad dream. Because for as long as humans have been able to count, they've been chasing problems that just refuse to be solved. Problems that mock us, problems that tempt us, and problems that probably caused more than one mathematician to pull out their hair at 3 in the morning and say, "Why did I choose this career again?" Let's start with one of the oldest and most famous, squaring the circle. It sounds so simple, right? Take a circle, draw a square with the same area. How hard can it be? You've got a compass, you've got a ruler, you've got at least 3 hours before your goat needs milking again. This was the obsession of ancient Greek mathematicians. They tried every trick they could think of. For centuries, generations of brilliant minds went after it. Spoiler alert, it is impossible. You cannot, using only straight edge and compass, make a square with the same area as a given circle. But they didn't know that back then, so they wasted lifetimes trying, which is kind of beautiful and kind of tragic at the same time. It's like watching your friend try to microwave pizza rolls without exploding them. You know it won't work, but you also kind of admire the determination. Another legendary headache, Fermat's last theorem. This one is spicy. In the 1600s, Pierre de Fermat scribbles in the margin of his book, "I have discovered a truly marvelous proof of this proposition, which this margin is too narrow to contain," and then he just walks away from history. He claimed that there are no 3 positive integers, a, b, c, that can satisfy the equation a to the n plus b to the n equals c to the n for any integer n greater than 2. Basically, no neat little Pythagoras triangles for higher powers. And he said he had the proof. Did he? Probably not. Did he care? Probably also not. But what followed was centuries of mathematicians trying, failing, obsessing. It became the Mount Everest of math. And what's funny is that it wasn't even officially proven until 1994 by Andrew Wiles, after more than 350 years of sleepless nights by countless mathematicians. Just imagine all those centuries, thousands of people sweating over Fermat's doodle, the ultimate math troll. Unsolvable problems are kind of like math's version of ghost stories. They travel from one generation to the next. Everyone takes a swing. No one ever really wins. They hang over math like a dark cloud, but they also pull people in like moths to a light bulb. The harder the problem, the stronger the obsession. Why? Because humans are wired that way. We hate leaving puzzles unfinished. We can't stand mysteries. It's like when Netflix drops a new show and you swear you'll just watch one episode. But at 4 in the morning you're on season 3, and your brain is like, "We must know." That's how it works with math. But the thing with math is, the cliffhanger can last not for one night but for centuries. And sometimes the story isn't just about the problem, but about the people who get swallowed up by it. Let's take Gödel, for example. In the 20th century, he drops a bombshell called the incompleteness theorem. It basically says there will always be true statements in math that cannot be proven. That's right, math, the very thing we thought was pure logic, turns out to have blind spots built into its DNA. It's like buying the world's most advanced car and then finding out it doesn't have reverse gear. Gödel proved that math itself is full of questions that are unsolvable by design, which is kind of terrifying but also kind of hilarious because mathematicians spend their lives trying to solve problems in a universe where unsolvable ones are guaranteed to exist. Or take the story of Ramanujan, the self-taught genius from India. He lived in the early 1900s, and he saw math in visions, almost like dreams. He wrote down incredible results, many of which he couldn't fully prove, but which turned out to be true. His notebooks are still being studied today. Imagine being so gifted that your casual scribbles in the margins are still keeping people busy 100 years later. But the flip side is that his obsession consumed him. He worked relentlessly, often in poor health, chasing math like it was a divine calling. These stories remind us that behind every theorem is a human being, sometimes brilliant, sometimes eccentric, often exhausted, and very often hilariously frustrated. Now here's the funny thing. For every unsolvable problem, there are 1,000 small human hacks. People invent new tools to make progress. The abacus, algebra, geometry tricks, all ways of getting a handle on the slippery monster that is mathematics. But those tools, as amazing as they were, always had limits. The Greeks couldn't square the circle, medieval scholars couldn't solve quintic equations, and modern mathematicians still can't tame the Riemann hypothesis. It's a never-ending cycle of hope, struggle, despair, and coffee. But think about it. Isn't that what makes math such a human story? It's not just about numbers on a page. It's about ambition. It's about stubbornness. It's about people standing up to the universe and saying, I bet I can figure you out, even if they absolutely cannot, even if they spend their whole lives chasing a proof that isn't even possible. There's something deeply human in that. It's tragic and funny at the same time, like trying to argue with your cat. You're not going to win, but you try anyway, because you're human. And so across centuries, from ancient Greece to modern universities, unsolvable problems piled up. Each generation inherited not just the knowledge of the past, but also the frustrations. You can almost picture mathematicians as a kind of relay race, handing the baton of unsolved problems forward. Here, I couldn't do it. Maybe you'll have better luck. And then centuries later, someone finally solves one, and the whole world cheers. And then we move on to the next impossibility. But here's the twist. While humans were banging their heads against these walls for hundreds, sometimes thousands of years, a new kind of mind was quietly being built. A mind made not of flesh and blood, but of circuits and code. A mind that doesn't need coffee, doesn't need sleep, and doesn't care if the problem is boring or repetitive or completely insane. And when that mind finally got pointed at math, well, things got interesting. Really interesting. Because the kinds of problems that kept humans busy for centuries turned out to be the kind of thing a machine could crack in weeks. And that's where our story is heading. But before we get to the machines, before we hand over the chalkboard to silicon brains, we need to understand just how deep the human struggle went. Because only then can we appreciate how shocking it is when a piece of code humming away in a server room suddenly does what we could not. For now, just remember this. Math has always had problems that mocked us, that laughed in our faces, that said you'll never solve me. And for centuries they were right. If you've ever stared at a math problem and thought, this is driving me crazy, congratulations, you've just joined a very old club. For as long as humans have been scribbling symbols on clay tablets or napkins or blackboards, math has had this strange ability to hijack the brain. It doesn't just confuse people. It doesn't just annoy people. It actually drives some of the smartest minds in history completely insane. And I don't mean in a ha-ha math is hard kind of way. I mean in a someone call a doctor because this guy hasn't eaten in 3 days. He's still writing equations on the walls kind of way. Take, for example, poor Kurt Gödel. We mentioned him before, but he deserves a spotlight here. Gödel was one of the most brilliant logicians of the 20th century, but he also lived on the edge of madness. He proved that mathematics is incomplete, that there are truths we can never prove. Imagine living with that knowledge in your head every single day. Imagine being the guy who looked inside the clockwork of logic and discovered missing gears. That will mess with your sanity. Toward the end of his life, Gödel was so paranoid that he believed people were trying to poison him. He refused to eat unless his wife prepared his meals, and when she became ill, he literally starved to death. That's what math can do. It can show you the limits of human reason, and once you've seen those limits, you can't unsee them. You just sit there staring into the abyss, and the abyss stares back with algebraic notation. And then there's Srinivasa Ramanujan, the genius from India. This man saw math not just as numbers but as visions. He would dream of mathematical formulas. He believed the goddess Namagiri whispered results into his ear at night. Imagine that. While most people dream of pizza or falling off a cliff, he dreamed of infinite series, but his obsession burned him up like a candle. He filled notebooks with formulas nobody understood at the time. Some of them were so far ahead of the curve that mathematicians are still proving them today. That's right. 100 years later, we're still catching up to the guy's doodles, but his health collapsed under the weight of his obsession. He spent days in a fever, scribbling equations that seemed to come from some other world. If math is supposed to be cold and logical, Ramanujan showed the other side. Fiery, mystical, dangerous, the kind of thing that can inspire but also consume you completely. But it's not just the tragic geniuses. Ordinary mathematicians throughout history have shown the same kind of madness, just in smaller doses. Have you ever tried to fall asleep but your brain keeps looping one tiny part of a problem, like a song stuck in your head? But it's not a song, it's a fraction that refuses to simplify. There's actually a name for this. Mathematicians call it mathematical insomnia. You can't rest because your brain won't let go of the puzzle. Think about that. Math literally robs people of sleep, which is ironic considering this channel is supposed to help you fall asleep. Maybe the whole trick is I'm just giving you other people's insomnia so you can feel relaxed about your own. Why does math drive people so mad? Partly because it's deceptive. On the surface, math problems look simple. You read the statement and think, oh, I can do that. Then you spend 4 years of your life screaming into a pillow. Fermat's last theorem looked innocent enough, right? Just a little equation. A to the n plus b to the n equals c to the n. Cute, easy, harmless. And then boom, 350 years of global obsession. Mathematicians just can't resist that trap. It's like someone leaving a mysterious box in your living room with a note that says, "Do not open." Are you kidding me? Of course you're going to open it. And of course it's going to ruin your life. Another reason math is so maddening is because it demands perfection. In most areas of life, close enough is fine. If you paint a picture and it's 90% done, it still looks good. If you cook a meal and it's 90% correct, people will still eat it. If you tell a joke and 90% of the audience laughs, that's a win. But in math, 90% is failure. A proof is either airtight or it's garbage. There's no middle ground, which means mathematicians can spend years thinking they're onto something, only to discover a tiny flaw that ruins everything. Imagine building a house for 10 years and then finding out the whole thing collapses because you forgot one nail. That's math. And then there's infinity. Infinity is the ultimate madness machine. Humans are not built to understand infinity. We can't picture it. We can't hold it in our heads. But math throws it at us constantly. Infinite series, infinite sets, infinite dimensions. Trying to grasp infinity is like trying to hug a cloud. It slips right through you, but you keep trying anyway, because maybe this time it will make sense. And while you're busy hugging the cloud, your sanity quietly packs its bags and leaves. Some of the funniest stories in math are about people who just couldn't let go. There's the tale of Paul Erdos, the eccentric Hungarian mathematician who literally wandered the world with a suitcase, crashing on couches, trading proofs for coffee, and staying up all night obsessing about problems. He once said, "A mathematician is a machine for turning coffee into theorems," which is funny until you realize he meant it. He lived on caffeine and stimulants, constantly chasing problems. When friends begged him to stop taking amphetamines, he agreed to quit for a month. After the month, he said, "You've set mathematics back a month." That's the level of obsession we're talking about. Math wasn't just a subject to him, it was oxygen. And here's the punchline. The rest of us are not immune. Maybe you're not Gödel or Ramanujan or Erdos. Maybe you're just some kid staring at algebra homework. But the madness is still there, just scaled down. You try one problem, you fail. You try again. Hours pass. You're muttering at your paper like it's a personal enemy. That little taste of madness, that's the same flavor that haunted the greats. Congratulations. You are now part of a long, noble tradition of losing your mind to math. So yes, math problems drive humans mad. They always have. They probably always will. Because the harder the problem, the more our brains latch onto it. It's not logical, it's not healthy, but it's human. And that's why, when machines eventually step in and start solving the problems that tormented us for centuries, it feels so strange. It's like watching someone walk calmly into the haunted house that terrified you as a child, and they just say, "What? It's fine, there's nothing here." And you're left standing outside thinking, but I lost my mind in there." That's the story we're building toward. Machines that don't get mad, don't get tired, don't dream of infinity. Machines that don't care if the problem is unsolvable to us. But to really feel the shock of that, you have to see just how deep the madness goes on the human side. And believe me, it goes deep. Entire lives consumed. Brilliant minds unraveling. All because of little puzzles that sit there on the page, smiling innocently, waiting for the next victim. So the next time math keeps you awake at night, don't feel bad. You're in good company. Some of the greatest names in history were right there with you, pacing their rooms, scribbling on scraps of paper, mumbling to themselves. Math is not just numbers. Math is a strange kind of madness that humans willingly walk into, again and again. And that madness, my sleepy friends, is the heart of the story. Before we dive into computers and artificial intelligence, let's slow down and talk about the very first math tools humans ever invented. Because here's the thing. Math didn't just happen in people's heads. From the start, we've needed gadgets, tricks, and hacks to keep our brains from exploding. And trust me, our brains are not built to juggle numbers on their own. We needed help. We needed shortcuts. We needed tools. And so, a long time ago, in a world with no smartphones, no calculators, not even a cheap Casio watch, the abacus was born. Now, the abacus might look like a children's toy, just some beads sliding on sticks, but don't underestimate it. This little contraption was the iPhone of the ancient world. It let merchants add and subtract faster than most people today can with a calculator. And it's old, really old. Versions of the abacus go back more than 4,000 years. The Sumerians had one. The Chinese perfected it. The Romans carried portable versions around, like the first pocket calculators. Imagine a Roman accountant pulling out his abacus at the market, beads clacking while yelling at someone about grain prices. It's kind of hilarious, but it worked. And the wild thing, people today still use the abacus, especially in parts of Asia. In fact, some kids trained on an abacus can do calculations faster in their head than you can on your phone. That's right. 4,000 years later, the abacus still holds up. Meanwhile, half of us can't even remember our PIN code. Progress is a funny thing. But humans didn't stop with beads on sticks. We moved on to symbols, to real notation, because numbers alone are messy. Try writing a complicated equation in Roman numerals. You'll give up halfway. That's why we invented algebra. Algebra is basically the idea that you don't always need the actual number. You can use letters to stand in for numbers you don't know yet. It's like the math version of insert name here. And this idea, simple as it sounds, changed everything. Algebra came out of the Islamic Golden Age around the 9th century. A brilliant Persian mathematician named Al-Khwarizmi wrote a book called The Compendious Book on Calculation by Completion and Balancing, which is not a title that screams bestseller, but it was revolutionary. He explained how to solve linear and quadratic equations using rules instead of guesswork. And the word algebra actually comes from the Arabic word al-jaba, meaning reunion or restoration. Fun fact, Al-Khwarizmi's name also gave us the word algorithm. So basically, without this guy you wouldn't have algebra homework, but you also wouldn't have Google search. It's a trade-off. And algebra wasn't just some abstract game, it had real uses. Merchants needed it for trade, architects needed it to build fancy domes, astronomers needed it to map the heavens. Algebra made the world more predictable, more controllable. Suddenly, problems that once looked impossible could be cracked with a few clever moves. It was like math leveled up, from stone tools to iron swords, but in number form. But here's the thing, early math tools weren't always foolproof. They sometimes made life more confusing. People didn't always agree on the best way to write numbers. The Greeks loved geometry, drawing shapes everywhere. The Babylonians used base 60, which is why we have 60 minutes in an hour. The Romans used numerals that were basically decorative art projects. And then when zero came along, it caused chaos. Yes, zero. The number that means nothing almost broke civilization. European scholars argued for centuries about whether zero should even count as a number. Some people thought it was suspicious. Like, how can nothing be something? How can a symbol for emptiness be useful? Imagine being scared of zero. But in a way, it makes sense. Zero is weird. It's nothing and everything. It's the key to place value, to decimals, to modern math. Without zero, algebra would be impossible. But humans didn't figure that out right away. It took time, a lot of time. So you can see a pattern here. Humans were desperate for ways to control math, to tame it, to make it less painful. The abacus helped, algebra helped, zero helped. But each step forward also came with confusion, with fights, with stubborn resistance. Change is hard, even in math, especially in math. Every new tool felt like a leap into the unknown, and humans are not great with unknowns. We like certainty, we like answers, but math kept reminding us that the path to certainty is full of arguments and mistakes. Want a funny example? Back in the Middle Ages, mathematicians were obsessed with solving cubic equations. They knew how to solve quadratics, thanks to Al-Khwarizmi. But cubics? Nope. And then in Italy, around the 1500s, a mathematician named Tartaglia figured out a way. But instead of publishing it, he kept it secret. Because math back then was competitive. They held public contests, like math duels, where two mathematicians would challenge each other with problems in front of a crowd. And if you lost, your reputation was ruined. So Tartaglia kept his method hidden, using it to beat rivals in these contests. Until, of course, another mathematician tricked him into revealing it. The story has betrayal, drama, and yes, math. Who said equations can't be juicy? These stories show that math tools aren't just about calculation. They're about culture, ego, and survival. The abacus was about trade. Algebra was about power and science. And zero was about whether you trust nothing. Literally. And through it all, humans pushed forward, one invention at a time, always trying to outsmart the universe. And maybe that's the bigger point. Humans are not built for raw math. We don't like huge numbers. We don't like endless precision. Our brains are squishy, emotional, easily distracted, so we invent tools. We externalize the hard stuff. We hand it to beads, to symbols, to algorithms. It's almost like math has always been too big for us, and the only way we've survived is by outsourcing the workload, first to abacuses, then to algebra, then to calculators, and eventually to machines. Every step makes us a little more powerful, but also a little more dependent. And that dependence sets the stage for what's coming later in our story, because if you hand enough of math over to a machine, eventually the machine stops being your assistant and starts being the genius in the room. But before we get to that future, it's worth pausing to admire the first steps, the humble beads on sticks, the strange little symbols in Arabic texts, the controversial nothingness of zero. These were the building blocks. Without them, the story of math and the story of AI solving math in weeks would never have happened. So next time you look at an equation and groan, remember this. Somewhere out there 4,000 years ago, a merchant was sliding beads on an abacus and groaning too. Somewhere in Baghdad, 1,200 years ago, a student was sweating through algebra problems and muttering under his breath. Somewhere in Europe, a monk was staring at a zero and thinking, "This can't be right. You are not alone." The frustration is ancient, the tools are ancient, but so is the progress. Math has always been a tug-of-war between confusion and clarity, and every tool we invented pulled us just a little closer to clarity, even if it drove us a little bit mad along the way. If the history of math were a TV series, the 17th and 18th centuries would be that one dramatic season where everything happens at once. Suddenly the cast expands, new plot twists drop every week, and the budget for explosions triples. This was the golden age of math, the era of Newton, Leibniz, Euler, and a whole crowd of geniuses who basically turned the world into one giant puzzle book. Problems that had mocked humans for centuries suddenly started cracking open. New problems appeared like hydra sprouting new heads, and math transformed from a collection of dusty tricks into a powerful engine driving science, engineering, and even politics. Let's start with Isaac Newton, the man who looked at an apple and somehow invented calculus. I mean, most of us see an apple and think snack. He saw an apple and thought, I should probably invent a new branch of mathematics to explain gravity. That's the kind of overachiever energy we're dealing with here. Newton's calculus gave humanity a way to describe motion, change, and curves in a precise way. For the first time, you could calculate not just where something is, but where it will be. You could predict the planets. You could predict cannonballs. You could predict your friend's beer mug sliding off the tavern table. It was mind-blowing. But of course, Newton wasn't alone. Enter Gottfried Wilhelm Leibniz, the German philosopher who also invented calculus, completely independently at the same time, because the universe has a sense of humor. What followed was one of the pettiest, nastiest academic feuds in history. Newton and Leibniz spent years accusing each other of plagiarism. Their followers fought like rival fan bases on Twitter. To this day, historians argue about who deserves more credit. Honestly, they both do. But try telling Newton that. He once described Leibniz as a man of loose morals, which in 1700s academic language was basically calling someone a troll. The feud wasn't pretty, but the math that came out of it changed the world forever. And then there was Leonhard Euler, the Swiss powerhouse who makes everyone else look lazy. Euler was like the Michael Jordan of math, except he never retired. He published more than 800 papers and books. His collected works fill over 70 volumes. To put that in perspective, if you started writing math papers today and never stopped, you still wouldn't catch up to Euler unless you had several lifetimes and a coffee IV drip. The man discovered formulas for everything. He connected geometry, algebra, trigonometry, number theory, you name it. And he did it all while slowly going blind. By the end of his life, he was almost completely blind, yet still producing groundbreaking work from memory. Imagine being so good at math that you don't even need to see numbers to manipulate them. Absolute legend. What made this era the golden age wasn't just the individuals, it was the sheer flood of new ideas. Suddenly people were measuring the Earth with unprecedented accuracy. They were charting maps of the world, calculating orbits, designing machines, building bridges. Problems that had felt mystical and unreachable started turning into solvable puzzles. And once one puzzle was solved, 10 new ones popped up. Math was exploding in every direction like a fireworks show that never stopped. But here's the funny thing. Even in this golden age, the madness never went away. Mathematicians still obsessed, still battled, still argued like kids fighting over toys. Newton locked himself in his room for months at a time, barely eating, scribbling proofs like a man possessed. Leibniz got dragged into endless disputes about whether infinitesimals were real or just philosophical nonsense. Euler calmly solved problems his colleagues thought were impossible, and then casually moved on to the next one, like someone finishing a crossword puzzle over breakfast. The Golden Age didn't make math easy, it just made the playground bigger. One of my favourite puzzles from this era is the 7 bridges of Königsberg. The city of Königsberg in Prussia had 7 bridges crossing its river. The question was simple: can you take a walk through the city, crossing each bridge exactly once? People tried for years, scribbling maps, trying routes, failing every time, and then Euler stepped in. He didn't just solve the puzzle, he invented graph theory in the process. He proved that the walk was impossible, which is hilarious. People spent all this time looking for a path that didn't exist. Euler basically said, guys, stop, it's literally not possible, go home. And then because he was Euler, he built an entirely new branch of mathematics out of the failure. That's the Golden Age in a nutshell. Even impossibility became fuel for progress. Another iconic moment was the solution of cubic and quartic equations. For centuries, mathematicians knew how to solve quadratics, those nice little parabolas from high school. But cubics, quartics, nope. And then Italian mathematicians in the 1500s and 1600s started cracking them. Remember Tartaglia, the guy with the secret method for solving cubics? This was the era when math duels were a thing, and solving equations wasn't just academic, it was competitive sport. Imagine 2 mathematicians facing off in front of a crowd, like gladiators, but instead of swords they had chalk. Whoever solved the hardest problems won fame and fortune. That's how high the stakes were, and these solutions laid the groundwork for the Golden Age explosion that followed. But the Golden Age wasn't just about solving equations, it was about asking deeper questions. What is a function? What does it mean for something to be continuous? Can you describe infinity in a rigorous way? The answers to these questions set the stage for modern analysis, for topology, for all the strange and beautiful math that came later. The Golden Age was like humanity stretching its brain and realizing, oh wow, this thing can go way farther than we thought. And of course, this was also the age of practical math. Engineers used calculus to design better ships. Astronomers used it to predict eclipses. Map makers used trigonometry to redraw the world. Finance people used probability to gamble with slightly more intelligence. Everywhere you looked, math was sneaking into the picture, shaping reality. What had once been a playground for curious monks and philosophers was now powering empires. But maybe the best part of this golden age is how human it all feels. We remember Newton, Leibniz, Euler as gods of math, but they were still just people. Newton was famously cranky, easily offended, and probably spent too much time indoors. Leibniz was a dreamer, bouncing between philosophy, law, and math, often annoying everyone around him. Euler was this calm, cheerful guy who somehow stayed productive while everyone else was fighting. They weren't superheroes. They were just humans with obsessions, flaws, and endless curiosity. And somehow, out of their quirks and rivalries, math leapt forward. So when we call it the Golden Age of Puzzles, it's not because math became easy or tidy, it's because math became alive. Problems weren't just abstract riddles anymore. They were tools for building the modern world. They were battlegrounds for egos. They were stepping stones to new branches of thought. It was messy, chaotic, brilliant, and deeply human. And that's the stage we need to set before moving on, because soon humans would start running into walls again. The puzzles would get harder, the solutions would slip away, and after this burst of golden light, math would once again start to mock us. The Golden Age was glorious, but it wasn't the end of the story. It was just the warm-up. So far, our story has been full of breakthroughs. Humans invent tools. Humans solve puzzles. Humans look very proud of themselves. The Golden Age gave us calculus, functions, Euler casually solving the seven bridges problem while blind. But then something happened. Math started fighting back. The 19th and early 20th centuries became the century of impossible proofs. Problems weren't just hard anymore, they were unsolvable, unprovable, and in some cases, fundamentally broken. It was like math raised an eyebrow at humanity and said, "Cute effort. Now watch me destroy your confidence." Let's start with David Hilbert, one of the most influential mathematicians of the early 1900s. In 1900, he gave a famous speech in Paris, listing 23 unsolved problems. These were not little puzzles. These were mountains. Conquering them would define the next century of mathematics. Hilbert was optimistic. He believed every problem could be solved with enough creativity and time. His motto was, "We must know, we will know," which sounds inspirational until you realize how savage the universe is about crushing human optimism. Because just a few decades later, Kurt Gödel showed up and said, "Actually, no, you won't." Gödel's incompleteness theorem proved that in any consistent mathematical system, there are true statements that cannot be proven. Think about that. Math itself has blind spots. There will always be truths you can never reach. It was like discovering that the map you've been using has missing cities, and no matter how hard you search, you'll never find them. Gödel essentially told Hilbert, "Sorry buddy, your dream of solving everything? Not happening." You can imagine Hilbert's ghost somewhere groaning. Gödel's result wasn't just shocking, it was existential. People had believed that math was the purest form of logic, a system where everything could be deduced if you just worked hard enough. And then Gödel came along and blew a hole in that idea. He showed that no matter how far you climb, there's always another cliff, always another unreachable truth. That realization shook mathematicians to their core. Some embraced it, others despaired. Some probably just went for a long walk and didn't come back. But Gödel wasn't the only one ruining everyone's day. Enter Georg Cantor in the late 1800s, the man who dared to mess with infinity. People already found infinity stressful. Cantor made it worse by proving that there are actually different sizes of infinity. There's infinity, and then there's bigger infinity, and then even bigger infinity. Infinity was supposed to be the ultimate concept, the end of the road. Cantor basically said, no, infinity has neighborhoods, and some are fancier than others. It was brilliant, but it also drove him to a breakdown. Cantor spent much of his later life in and out of mental institutions, crushed under the weight of the infinite. Which sounds poetic, but it's also kind of heartbreaking. Then there was the Riemann hypothesis. Bernhard Riemann, another 19th century genius, proposed a conjecture about the distribution of prime numbers. He suggested that all the non-trivial zeros of the Riemann zeta function lie on a certain line. If you don't know what that means, don't worry. Neither did most of his contemporaries, but it turns out this conjecture underpins huge parts of number theory. To this day, nobody has proven it. It's like the boss level of math. If solved, it could unlock secrets about primes, cryptography, even the stability of the universe. And if it's false, well, let's not think about that. The point is, it has resisted proof for over 160 years. Mathematicians have thrown armies of brains at it, and the hypothesis just sits there smirking. These impossible proofs piled up. Fermat's last theorem, finally solved in the 1990s, had mocked humans for 350 years. The four-color theorem, about coloring maps, turned out to need computer help to prove. Problems kept appearing that didn't bend to human will. Instead of solutions, mathematicians found walls, thick, unbreakable walls. And it wasn't just the problems, it was the very structure of math. Imagine being told that the subject you've devoted your life to has fundamental holes, that perfection is impossible, that certainty is a dream. It messed with people's heads. The 19th century began with optimism. By the early 20th century, math had become a psychological thriller. The irony is that this era produced some of the most beautiful mathematics ever. Non-Euclidean geometry, set theory, topology, all blossomed during this time, but each came with its own paradoxes, its own frustrations. For every triumph, there was a new reminder of human limits. For every solved puzzle, 3 more impossible ones appeared. And that's why this period is so fascinating. It wasn't just a time of progress. It was a time of humility. Humanity realized that math was bigger than us, stranger than us, and not something we could fully control. We weren't the masters of numbers. We were just explorers in a labyrinth, with walls that moved when we weren't looking. Of course, mathematicians being mathematicians, they didn't quit. They doubled down, they obsessed even harder. They lost more sleep, drank more coffee, scribbled more furious notes. That's the spirit of math. Even when it tells you you can't win, you keep playing. It's madness, but it's also beautiful madness. And this madness sets the perfect stage for what happens later. Because while humans were banging their heads against impossible proofs, machines were quietly getting stronger. At first they were just calculators. Then they became computers. Then they became something new entirely. And one day, while humans were still obsessing over Hilbert's problems and Riemann's line of zeros, an AI would stroll into the room, glance at a centuries-old puzzle, and solve it in weeks. That's the punchline we're heading toward. But to appreciate it, you need to feel the frustration, the despair, the centuries of impossible proofs that drove humans mad. So yes, the century of impossible proofs wasn't just about failure. It was about setting the stage for the ultimate twist. Humans tried, humans struggled, humans failed, and then the machines arrived. Some math problems don't just sit there politely waiting to be solved. No, some math problems actively mock us. They sit on the page like tricksters, grinning while humans sweat, cry, and grow old trying to defeat them. These are the problems that seem simple at first glance, but reveal themselves to be monsters once you dive in. They are the mathematical equivalent of that one IKEA screw that never fits anywhere but somehow prevents you from finishing the entire piece of furniture. Let's meet a few of them. First up, the Collat's conjecture. This one is so innocent, it's almost insulting. Take any positive number. If it's even, divide it by 2. If it's odd, multiply it by 3 and add 1. Repeat. The conjecture says no matter what number you start with, you will always eventually reach 1. That's it. Sounds simple, right? People have tested it with trillions of numbers, and so far, it always ends at 1. But has anyone proved it? Nope, not even close. The Collat's conjecture just keeps dangling there, mocking us with its simplicity. Mathematicians have called it utterly unsolvable, and a conspiracy by the devil to drive humans insane. Imagine centuries of geniuses defeated by a problem so easy you could explain it to a child in 30 seconds. That's Collat's for you. Then there's the Riemann hypothesis, which we touched on earlier. This one doesn't even bother to pretend to be friendly. It's the boss level of math. It says something deep about the distribution of prime numbers, and if true, it underpins much of modern number theory. If false, well, let's hope it's not false, because then a lot of math collapses. The Riemann hypothesis is like a landlord who may or may not exist, but everyone keeps paying rent anyway, just in case. And the worst part? Nobody knows if the landlord is real. Another mocking problem, the P versus MP question. This is the riddle of riddles in computer science and math. It asks, if you can quickly verify the solution to a problem, can you also quickly find the solution? Sounds like a nerdy detail, but the consequences are enormous. If P equals MP, then problems we thought were impossible to solve efficiently suddenly become solvable. Cryptography collapses, online banking dies, secret codes vanish. But if P does not equal MP, then we go on as usual, but with no satisfying proof to make us feel better. People have been debating this since the 1970s, and it still sits there smirking. It's the problem equivalent of someone asking, "Are we there yet?" for 50 years straight. Let's not forget the twin prime conjecture. Are there infinitely many pairs of prime numbers that are just 2 apart, like 11 and 13 or 17 and 19? Seems reasonable. Nobody can prove it. Mathematicians have gotten close, showing that there are infinitely many primes that are within 246 of each other, which is like answering, are there infinite twin primes? With no, but there are infinite cousins, roommates, and people who live in the same apartment block. The twin primes are still laughing at us from across the street. And then there's the riddle of the perfect cuboid. This one asks, is there a rectangular box where all edges, face diagonals, and the space diagonal are whole numbers? Mathematicians have searched for centuries, nobody has found one, and nobody has proven they don't exist. The problem just sits there like a prank box. Either it's hiding the perfect cuboid somewhere deep in the number jungle, or it's mocking us with eternal emptiness. Either way, it refuses to give a straight answer. What makes these problems so cruel is not just their difficulty, it's their personality. They tease, they lure you in with a simple setup. Then they devour your free time, your social life, and your sanity. They're like riddles from a mischievous sphinx. Oh, you thought this would be easy? How adorable. See you in 30 years. There's even a whole set of these known as the Millennium Prize problems. In the year 2000, the Clay Mathematics Institute offered $1 million each for the solution to 7 specific problems. Big names like the Riemann hypothesis and P versus NP are on the list. As of now, only one has been solved, the Poincare conjecture, about the shape of three-dimensional space. It was solved by a Russian mathematician named Grigory Perelman, who then famously refused the prize money and vanished from the spotlight. Imagine being so good at math that you solve a century-old problem, win $1 million, and then just say, "Nah, I'm good." The rest of the problems are still sitting there, laughing at us. But maybe the cruelest part is this. Some problems remain unsolved, not because they're impossible, but because nobody knows how to approach them. They're like locked doors without even a keyhole to fiddle with. You just stand there, staring, hoping one day someone figures out where the key is hidden. Until then, the problems mock you from the other side of the door. And it's not just professional mathematicians who feel the sting. These mocking problems trickle down into everyday life. They show up as paradoxes, riddles, or unsolved mysteries that ordinary people hear about in school or see on YouTube. They lodge themselves in your brain and won't let go. Maybe you'll lie awake at night thinking about collets. Maybe you'll stare at your ceiling wondering if twin primes go on forever. The problems don't care who you are. They'll mock anyone, from the most decorated professor to the sleep-deprived student. But here's the thing. Even though these problems mock us, we love them. Humans are weird like that. We love the chase. We love the unsolved. The mocking is part of the thrill. If math gave up all its secrets too easily, maybe we'd get bored. Maybe we'd stop looking. The problems keep us hooked, like a cliffhanger that never ends. And who doesn't love a good cliffhanger? Still, it's humbling. After centuries of genius, after building calculus, topology, set theory, after creating entire worlds of math, we still get stumped by problems that look like they belong in a high school worksheet. The Collatz conjecture could be written on a sticky note. The twin prime conjecture fits in a tweet. And yet they mock us, decade after decade, generation after generation. And that's why the arrival of AI is so dramatic. Because while humans have been laughed at by these problems for centuries, machines don't feel mocked. They don't get frustrated. They don't lose sleep. They just chew through patterns tirelessly, endlessly, and sometimes they find the crack in the wall that humans couldn't. That's why when AI solves a problem in weeks that mocked us for centuries, it feels like an insult. Like the problem was never mocking math itself, it was mocking us. So next time you hear about an unsolved problem, don't just see it as abstract. See it as a personality. A prankster, a trickster, a little gremlin sitting in the corner of mathematics, waiting for the next victim. And if you find yourself obsessing over it, remember, you're not alone. Mathematicians throughout history have been mocked too. Some laughed, some cried, some gave up, and now maybe some will let the machines take over the fight. When we think of mathematicians, we often imagine these flawless beings who live in a world of pure logic, sitting in candlelit studies proving theorems with perfect precision, cold, logical, untouchable. But let's be honest. Mathematicians are human, and humans cheat. Not cheat in the sense of sneaking notes into an exam, but cheat in the sense of bending the rules, finding shortcuts, and pretending close enough is the same as victory. Behind the polished image of math, there's a messy world of approximations, heuristics, and workarounds. And honestly, without these cheats, civilization probably wouldn't exist. Take pi, the famous number that never ends. Mathematicians have been obsessed with pi for thousands of years, but you can't write it down exactly. You can't ever know all of it. So what did ancient mathematicians do? They cheated. The Egyptians used 256 over 81, which is about 3.16. The Babylonians used 25 over 8, which is 3.125. Archimedes got fancy and trapped pi between two fractions, 223 over 71 and 22 over 7. 22 over 7, there's your classic cheat. Even today, people still use it as an approximation. Every time you calculate with 22 over 7, you're technically lying, but it's a convenient lie, and the world runs on convenient lies. Or take square roots. Before calculators, finding the square root of a number was a nightmare, but mathematicians developed algorithms that gave answers close enough. You didn't need 10 decimals when you were trying to build a temple. If the stone fit, the approximation worked. That's cheating in the best way. Math isn't always about perfection. Sometimes it's about not letting the building fall down. And then there's probability. When people started studying chance in the 1600s, they quickly realized that exact calculations were often impossible. So they leaned on estimates, assumptions, and hand-wavy reasoning. This outcome is likely. That outcome is unlikely. So let's bet accordingly. It's the math version of guessing, but with enough polish to sound impressive. And it worked. Entire casinos run on this kind of cheating. Insurance companies too. You pay your monthly fee, not because someone knows your exact future, but because they've cheated with probabilities and decided you're worth a certain risk. Comforting, right? Even the greats cheated. Newton, the guy who invented calculus, sometimes used what were basically infinite fudge factors called infinitesimals. They weren't rigorously defined at the time. They were more like magical dust sprinkled on problems to make them work out. Critics accused Newton of dark mathematical witchcraft. Later, mathematicians cleaned it up and made it rigorous. But for centuries, calculus was built on what was essentially a cheat code. Without that cheat, we wouldn't have physics, engineering, or your GPS. Another classic cheat is numerical methods. That's a fancy way of saying we can't solve this exactly, so let's approximate it with a computer or a table. Want to know the trajectory of a rocket? Good luck solving the equations exactly. They're too messy. But with numerical methods, you break the problem into small steps and let a machine chew through it. It's not exact, but it's good enough to land people on the moon. So yes, the space race was won with math cheats. Mathematicians also cheat with models. Reality is too complicated, so they simplify it. Want to model the economy? Assume people act rationally, even though they clearly don't. Want to model a planet? Pretend it's a perfect sphere, even though it's lumpy. These models are lies, but they're useful lies. George Box, a famous statistician, once said, "All models are wrong, but some are useful." That's the ultimate math cheat philosophy. Don't let the truth get in the way of something that works. Even proof sometimes cheat. Mathematicians use something called heuristics. A heuristic is basically a smart guess. It's when you don't have a rigorous proof, but you have enough evidence to believe something is true. It's like saying, "I don't have receipts, but trust me, I know what I'm talking about." Entire fields have been built on heuristics that were later proven, or sometimes disproven centuries later. Heuristics keep the train moving even when the tracks aren't finished. And of course, there's the most human cheat of all, ignoring inconvenient details. Mathematicians will sometimes say, "Assume without loss of generality," which is code for, "Let's pretend this detail doesn't matter so I can get to the good part." And sometimes it works, sometimes it doesn't. But hey, it makes the proof look cleaner. Every time you see that phrase, remember, it's a little wink, a little cheat, a little don't look behind the curtain. But here's the thing. Cheating in math isn't really cheating. It's survival. It's adaptation. If humans waited for perfect proofs before doing anything, we'd still be in caves arguing about how many rocks make a pile. Instead, we approximated, guessed, modeled, and fudged our way into civilization. Bridges stand, rockets launch, phones work, not because of perfect math, but because of good enough math. And that's kind of liberating. It means you don't have to be perfect either. The universe runs on cheats. Still, there's something funny about the image of mathematicians pretending to be pure and logical while secretly cutting corners like the rest of us. They'll publish a 200-page proof with phrases like, "It is obvious that," which usually means I have no idea how to prove this, but I hope nobody calls me out. They'll hide approximations inside elegant formulas. They'll make bold assumptions and sweep problems under the rug. And yet, somehow, the whole thing works. Civilization doesn't collapse. In fact, it thrives. And maybe that's why math is such a human story. Because for all the talk of logic and rigor, it's still shaped by the same instincts that guide the rest of us. We improvise, we hack, we cheat, and we laugh about it later, which makes the arrival of machines even more jarring. Because machines don't cheat, at least, not in the same way. They don't approximate unless we tell them to. They don't wave their hands and say obviously. They grind through the details with relentless patience, which means when AI steps into math, it's not playing the same game. It's not cutting the same corners. It's doing something alien. and that's why it can sometimes solve in weeks what mocked us for centuries. So yes, mathematicians secretly cheat. They always have. They probably always will. But don't think of it as a flaw. Think of it as humanity's survival strategy. Without cheats, math would be impossible. With cheats, math becomes livable, even useful. And if you've ever guessed on a test, rounded up a bill, or said close enough while building IKEA furniture, congratulations, you're part of the grand mathematical tradition of cheating your way through life. Infinity. Just the word makes people's brains hurt. We humans are not built for infinity. Our minds evolved to deal with small, cozy numbers. We can handle 1 apple, maybe 2 apples, maybe 7 apples if you're really good at juggling. But infinity, forget it. Infinity laughs at us. It's too big, too strange, too slippery. And yet for thousands of years, mathematicians have been poking at infinity, like curious children poking at a sleeping lion. Sometimes it stays quiet. Sometimes it wakes up and roars. Think about how limited we are. Psychologists say the average person can only hold about 7 things in working memory at once. 7. That's why phone numbers used to be 7 digits long. Your brain panics after that. Ask someone to remember a list of 15 groceries and watch them collapse. And yet infinity is the opposite of that. Infinity is not 7. Infinity is not 15. Infinity is forever. It's trying to fit the ocean into a shot glass. No wonder it makes us dizzy. The Greeks were some of the first to wrestle with infinity, and it nearly broke them. Zeno of Elea came up with paradoxes that still haunt philosophers today. His most famous one is Achilles and the tortoise. Achilles, the fastest man alive, races a tortoise. He gives the tortoise a head start. By the time Achilles reaches the tortoise's starting point, the tortoise has moved a little ahead. By the time Achilles reaches that point, the tortoise has moved a little farther, on and on forever. According to Zeno, Achilles never catches the tortoise. Infinity slices the race into endless pieces, and Achilles loses. Of course, in real life, Achilles smokes that tortoise in 2 minutes. But the paradox reveals the weirdness of dividing space and time infinitely. Our brains hate it. We want the race to end. Infinity won't let it. Later, mathematicians tried to tame infinity with calculus. Newton and Leibniz introduced infinitesimals, tiny, almost zero quantities that you could add up infinitely to measure curves and areas. It worked. It explained motion, gravity, planets. But it also freaked people out. How can you add up infinitely many things and get a finite result? It's like adding infinite slices of pizza and ending up with just one pizza. Our instincts scream, that can't be right. And yet calculus works so well we used it to land astronauts on the moon. Infinity may confuse us, but it also powers our greatest achievements. Then came George Cantor in the 19th century, and he took infinity to a whole new level. Cantor proved that not all infinities are equal. There are bigger and smaller infinities. For example, the infinity of whole numbers 1, 2, 3, and so on is one size, but the infinity of real numbers, like all the decimals between 0 and 1, is a bigger size. There are infinitely more numbers between 0 and 1 than there are whole numbers. Wrap your head around that. Infinity has levels. It has neighborhoods. It has a real estate market. Some infinities are mansions, others are studio apartments. This blew mathematicians' minds. It also drove Cantor himself into depression. He spent much of his later life in and out of mental hospitals, tormented by the very infinities he discovered. Infinity doesn't just mock us, it breaks us. Here's the problem. We keep trying to picture infinity, and we can't. We imagine a really big number, like a billion or a trillion, and we call it infinity. But infinity isn't a number. It's not the biggest number. It's the idea of no end, and our brains are not designed for no end. Our brains want beginnings, middles, and ends. Infinity refuses to give us that. It's like watching a movie that never stops. At first it's fun, then it's exhausting, then it's madness. Humans deal with this madness by cheating. We pretend infinity is something we can handle. We cut it into pieces. We use symbols like hammer to make it look tidy. We say things like limit as n approaches infinity, as if that means we've got infinity under control. But really, it's a linguistic trick. Infinity isn't controlled, it's just sitting there smiling while we try to domesticate it. And yet, infinity shows up everywhere. In geometry, in calculus, in probability. The number line stretches infinitely in both directions. The digits of pi go on forever without repeating. The universe itself may be infinite. Every time we think we can avoid infinity, it sneaks back into the picture. It's unavoidable. It's the gatekeeper of mathematics. If you want to play the game, you have to face infinity sooner or later. And of course, infinity drives people a little crazy, in fun ways too. Take Hilbert's Hotel, a thought experiment invented by David Hilbert. Imagine a hotel with infinitely many rooms, all occupied. You'd think it's full. But if a new guest arrives, you can still make space by moving the person in room 1 to room 2, the person in room 2 to room 3, and so on. Suddenly room 1 is free. Infinity makes space even when there is no space. And if infinitely many new guests arrive, no problem. Move everyone to the room with double their current number, freeing up infinitely many odd-numbered rooms. Infinity is the ultimate prankster. It breaks all the rules of common sense, and it does it with a straight face. But here's the twist. Even though infinity mocks us, we can't stop chasing it. It's irresistible. It's the final frontier. We know our brains aren't built for it, but we keep building ladders toward it anyway. Cantor built set theory. Newton built calculus. Modern mathematicians build ever more elaborate frameworks to handle infinities of all sizes. Each time it feels like we've tamed it. Each time infinity just laughs and reveals a new layer. And maybe that's the beauty of it. Infinity shows us our limits, but also our ambition. We know we'll never fully grasp it, but we keep trying. It's the ultimate unsolvable riddle, the ultimate cliffhanger, and maybe humans secretly love cliffhangers. Infinity drives us mad, but it also keeps us curious. Of course, machines don't care about infinity the way we do. For a computer, infinity is just an error message or an overflow. It just does not compute. AI doesn't stay awake at night wondering about the nature of endlessness. It just follows the rules it's given. That difference between our obsession with infinity and the machine's indifference is one of the reasons AI sometimes gets farther than us. Infinity mocks humans. Machines don't feel mocked. So yes, humans are not built for infinity. Our brains panic after 7. We try to hug infinity and fall flat on our faces. It's confusing, it's terrifying, and it has driven some of the greatest minds into madness. But it's also the reason math is so endlessly fascinating. Without infinity, math would be smaller, tidier, easier, and much more boring. Infinity is the impossible flavor we can never stop craving, even if it drives us a little crazy. Before machines started solving deep math problems and breaking the hearts of centuries of mathematicians, there was a smaller but equally important revolution, the calculator. And I don't just mean the little plastic box in your drawer that you only use to split the dinner bill. I mean the entire history of humans building devices to do the one thing our brains are really bad at, keeping track of numbers without messing up. Let's be honest, human brains are not good calculators. We forget, we get distracted, we lose count. Try counting to 1,000 without skipping or repeating, and you'll see what I mean. Somewhere around 347 your brain just fizzles. So of course, ancient humans started inventing tools. First came the abacus, which we've already met. Beads on sticks. Elegant, reliable, way cooler than people give it credit for. But the abacus was just the beginning. Fast forward to the 1600s, and you get John Napier, a Scottish mathematician who gave the world logarithms. Now logarithms are like a cheat code for multiplication. Instead of multiplying huge numbers directly, you just add their logs. Sounds dry, but this idea literally saved lives. Before calculators, navigators at sea used giant tables of logarithms to figure out their position. Imagine being lost in the middle of the ocean with nothing but a compass, a sextant, and a 400-page book of log tables. It sounds terrifying, but it worked. In a way, logarithms were the first mental calculator, compressing huge operations into something humans could actually handle. But Napier wasn't done. He also invented Napier's bones, a set of rods with numbers inscribed on them, like math chopsticks. You'd arrange them to multiply numbers. It was clunky, but it beat doing the math by hand. Napier basically looked at multiplication and said, "No thanks, I'll build a gadget," which, to be fair, is the most human response to any difficult problem. Then came Wilhelm Schickard, who built one of the first mechanical calculators in the 1620s. His device could add and subtract automatically. Sadly, the prototype was destroyed in a fire, because history loves drama. But the idea didn't die. A few decades later, Blaise Pascal built the Pascaline, a machine with little gears and wheels that could do addition and subtraction. His dad was a tax collector, so naturally Pascal thought, why not invent a machine to make dad's job easier, which might be the nerdiest act of teenage rebellion in history. Instead of sneaking out to parties, Pascal was at home building mechanical calculators. And then came Gottfried Wilhelm Leibniz. Yes, the same guy who fought Newton over calculus. Apparently fighting wasn't enough for him, so he also built the stepped reckoner, a calculator that could multiply and divide. Leibniz was obsessed with the idea of turning thought into a mechanical process. He once said, "It is unworthy of excellent men to lose hours like slaves in the labor of calculation," which is a fancy way of saying, math homework sucks, let's invent robots. Honestly, respect. By the 1800s, mechanical calculators were everywhere. Charles Babbage designed his famous difference engine, a massive machine powered by cranks and gears that could calculate polynomial functions. It was so ahead of its time that the British government gave him funding and then promptly regretted it when the project spiraled into endless prototypes. Babbage never finished building his machine, but his ideas laid the groundwork for computers. His collaborator Ada Lovelace even wrote what's considered the first computer program, all because humans were too lazy to multiply numbers by hand. Laziness really is the mother of invention. And of course, let's not forget slide rules. For centuries, slide rules were the go-to tool for scientists, engineers, and students. They look like rulers with sliding parts, but they use logarithmic scales to let you multiply, divide, and even calculate roots and trigonometry. They don't give exact answers, but they give good enough answers. Entire rockets were designed with slide rules. The Apollo missions to the moon? Powered by slide rules and coffee. That's wild. A stick with numbers on it took us to space. But the real revolution came in the 20th century, with electronic calculators. In the 1960s and 70s, companies like Texas Instruments and Casio started producing portable calculators, small enough to fit in your pocket. At first they were expensive. Buying one was like buying a small car. But soon the prices dropped, and calculators invaded classrooms. Teachers panicked, of course. If kids use calculators, they'll forget how to do real math. Which is funny, because people said the same thing about writing when the alphabet was invented. If kids use letters, they'll forget how to remember stories. Humans never change. But calculators didn't kill math. They liberated it. Suddenly, students could spend less time crunching numbers and more time thinking about concepts. Engineers could handle calculations that were previously impossible. Businesses could scale up. Everyday people could finally figure out the tip at dinner without embarrassing themselves. The calculator democratized math. It turned something that once required years of training into something you could do in seconds. And here's the bigger point. The calculator revolution wasn't just about convenience. It was a shift in trust. For centuries, humans trusted only their own brains, maybe an abacus, maybe a table of logs. Suddenly, we were handing over math to machines. That's a big deal. It set the stage for everything that came later. Computers, AI, algorithms. Once we got comfortable letting a box of circuits do our math, we opened the door to letting machines do much, much more. But the calculator revolution also raised an awkward question. If machines can do the grunt work faster and more accurately than us, what's left for humans? At first the answer was clear. Creativity, problem solving, deeper understanding. But as machines got smarter, the line blurred. That anxiety you feel when your phone autocorrects a word and you're not sure if you can still spell. Mathematicians felt that with calculators, wait, can I still multiply two big numbers without this thing? Am I becoming obsolete? Spoiler, no, but the worry was real. And that brings us back to the theme of our story. Humans tried for centuries to master math, and machines swooped in to help, first with abacuses, then mechanical calculators, then slide rules, then electronic calculators. Each step made us stronger, but also a little more dependent, and every step brought us closer to the moment when machines wouldn't just assist us, they would surpass us. So the next time you casually pull out your phone to calculate a 15% tip, remember, you are part of a long history of humans outsourcing math to gadgets. You're standing on the shoulders of Napier, Pascal, Leibniz, Babbage, and a million anonymous engineers. Your phone calculator is the descendant of centuries of clever hacks, shortcuts, and revolutions. And that humble act of pressing a few buttons? It's not just convenience. It's the continuation of humanity's greatest tradition, admitting we're bad at math and building a machine to do it better. By the mid-20th century, calculators were everywhere. They had already stolen most of the boring jobs from mathematicians, adding, subtracting, multiplying, dividing. Humans were relieved, but also slightly insecure. If a pocket-sized box could do the math faster than a professor, what would a real machine, a real thinking machine, be able to do? That's when people started dreaming about artificial intelligence. Not the kind of AI we know today with deep learning and chatbots, but early AI, clunky, optimistic, and sometimes hilarious. The story really starts in the 1950s. Computers had just been born. They were giant, humming beasts the size of entire rooms. They used vacuum tubes that overheated, punched cards that jammed, and memory so small your microwave has more computing power today. But even with these limitations, people immediately jumped to the big question: could a machine actually think? Alan Turing had already teased this idea in the 1940s. He asked, "Can machines think?" and proposed what became known as the Turing test. The idea was simple. If you have a conversation with a machine and can't tell whether it's human or not, then the machine is intelligent. Of course, back then the best computers could barely add two numbers without crashing. But the dream was there. Turing basically planted the seed. Machines could someday act like brains. By 1956, at a conference at Dartmouth College, the term artificial intelligence was officially born. The people there were wildly optimistic. They thought that within a few decades, machines would not just calculate, but reason, learn, and maybe even do original research. They wrote proposals saying things like every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. Translation: give us a summer and a grant and we'll build robot brains. Spoiler: no, they didn't. But you have to admire the confidence. In the 1960s, early AI systems started appearing. They weren't solving math's deepest mysteries, but they were impressive for the time. One famous program was eLaser, a chatbot that pretended to be a therapist by flipping your statements into questions. You'd type, "I feel sad," and eLaser would reply, "Why do you feel sad?" People were amazed. Some even thought the program understood them. In reality, it was just a clever script. But the illusion of intelligence was enough to spark excitement. If a simple program could mimic conversation, maybe deeper thinking wasn't far away. Another early AI dream was expert systems. These were programs that stored lots of rules and facts about a subject like medicine or engineering. You'd ask a question, and the system would apply the rules to give you an answer. It was like talking to a super-organized encyclopedia. For a while, this looked promising. Expert systems could actually outperform humans in narrow areas, but they were brittle. If the problem didn't fit neatly into their rulebook, they failed miserably. Still, they showed that machines could act like specialists, at least in carefully controlled situations. Mathematicians also dipped their toes into AI. They built theorem-proving programs like the logic theorist in the 1950s, which proved some of the theorems in a famous math textbook. Later, programs like Proof9 and Coct formalized proofs with machine precision. This was thrilling. Machines weren't just calculating anymore. They were reasoning in their own limited way. Of course, they mostly proved theorems humans already knew, but the idea was intoxicating. Maybe one day, a machine would prove something humans couldn't. But early AI also had its awkward teenage years. Researchers promised too much and delivered too little. Funding poured in, then dried up when results didn't meet expectations. This led to what people call the AI winters, periods when the hype crashed and nobody wanted to touch AI. The first winter hit in the 1970s, when it became clear that early approaches like symbolic reasoning couldn't scale up. Computers just weren't powerful enough, and the world wasn't neat enough to be described by endless if-then rules. The second winter came in the 1980s, after expert systems failed to live up to their hype. AI was like a band that released a couple of catchy singles but couldn't deliver a solid album. Still, the dreams never died. Writers and scientists kept imagining machines that could rival human thought. Sci-fi poured gasoline on the fire. HAL 9000 in 2001, A Space Odyssey, The Terminator, Star Trek's Data. These fictional AIs were smarter, faster, and sometimes scarier than humans. They made people both excited and nervous. On one hand, who wouldn't want a robot sidekick who can do all your homework? On the other hand, who wants to get replaced or worse, eliminated by a machine that doesn't need sleep? Through all of this, one idea kept people hooked. The thought that machines might eventually tackle the hardest problems we face. Problems that had mocked humans for centuries. If early computers could prove basic theorems, maybe future ones could go after giants like the Riemann hypothesis. The dream was alive even when progress stalled. Researchers looked at their clunky machines and thought, give us a little more power, and maybe, just maybe, we'll crack the uncrackable. And here's the funny part. Even in those early decades, people were already asking the same questions we ask today. Will machines replace humans? Will they surpass us? Will they understand beauty, creativity, humor? In the 1960s, Marvin Minsky, one of the founding fathers of AI, predicted that within a generation machines would be as smart as humans. That was overly optimistic. But you can't blame him. When you're standing at the dawn of something new, it's easy to think the sunrise will light up the whole world immediately. The truth was slower. Early AI dreams laid the foundation, but they didn't deliver the miracle. They gave us programs that could play checkers, chat awkwardly, and prove simple theorems. They gave us rule-based systems that looked impressive until they collapsed outside their comfort zone. They gave us the vision, but not yet the reality. Still, those dreams mattered. They set the stage for what came next. For the machine learning revolution, for the neural networks that finally lived up to the hype, for the moment when an AI would look at a centuries-old math problem, shrug, and solve it in weeks. So when we talk about early AI, don't laugh too hard at its failures. Yes, Eliza was just flipping your words back at you. Yes, expert systems were fragile. Yes, the AI winters were embarrassing. But without those awkward beginnings, we wouldn't have the AI we have today. Every chatbot, every algorithm, every problem-solving machine stands on the shoulders of those early dreamers who dared to believe a computer could think, even if their machines kept overheating and crashing on basic multiplication. And maybe that's the charm of it. Early AI wasn't about perfection. It was about imagination. It was humanity daring to believe that thought itself could be mechanized. It was clumsy, overconfident, and sometimes ridiculous. But it was also beautiful, because every great revolution starts with a dream that looks impossible. For most of history, humans were sure about one thing. Our brains were the ultimate problem-solving machines. Sure, calculators could crunch numbers, but they didn't think, they didn't strategize, they didn't imagine. If you wanted creativity, cunning, or the ability to outwit an opponent, you needed a human. And for a long time, the symbol of ultimate brain power wasn't mathematics, it was chess. A game so deep and so strategic that people thought no machine could ever truly master it. Spoiler, they were wrong. Chess has always had this aura of intellectual glamour. Kings and queens played it. Generals studied it. Nerds worshipped it. To be good at chess meant you had a sharp, powerful mind. So naturally, when computers came along, one of the first challenges people threw at them was, bet you can't beat us at chess. It was like humans collectively said, sure, you can multiply big numbers, but let's see you take down a grandmaster. In the beginning, computers were terrible at chess. Embarrassingly bad. They blundered pieces, fell for obvious traps, and generally looked like confused toddlers. A decent club player could demolish them, but computers had one thing humans didn't: patience. They could brute force possibilities, scanning move after move after move, long after a human brain would melt. All they needed was more power, and more clever programming. By the 1980s, chess programs were improving fast. They still weren't world-class, but they could beat ordinary players. Then came the 1990s, and IBM's Deep Blue, the first machine to go toe-to-toe with a world champion. In 1996, Deep Blue played Garry Kasparov, the greatest player of the time. Kasparov won. Humans celebrated. Machines were clever, but not that clever. 1 year later, they had a rematch. This time, Deep Blue won. A computer had officially beaten the best human at chess. It was the end of an era. If chess was the ultimate test of intelligence, then intelligence had just crossed over to silicon. Of course, looking back, Deep Blue wasn't really thinking like a human. It wasn't creative in the way Kasparov was. It just brute-forced millions of possibilities, guided by some clever evaluation rules. But that didn't matter. To the public, It felt like the machines had invaded human territory. Chess, the sacred temple of human intellect, had fallen. And here's where things get interesting for math. Because once computers proved they could conquer chess, people started asking, what about mathematics? Could a machine not just play games, but also prove theorems, solve puzzles, make discoveries? Math was supposed to be even harder than chess. Chess has rules, a finite board, a finite set of moves. Math is infinite. Math is abstract. Surely no machine could handle that, right? Well, not so fast. Even in the 1960s, programs were already proving simple theorems in logic. They weren't flashy, but they worked. Over time, more sophisticated proof assistants and automated reasoning tools appeared. They checked proofs line by line, with no room for human sloppiness. They weren't inventing grand ideas, but they were catching errors humans missed. And slowly the line between chess and math began to blur. If a machine could brute force chess moves, maybe it could brute force parts of math too. The funny thing is that humans kept underestimating computers. After Kasparov lost, people comforted themselves by saying, well, okay, but chess is just calculation. Humans are still better at Go. Go, the ancient board game from China, was supposed to be unbeatable by machines because it's astronomically more complex than chess. The number of possible Go positions is greater than the number of atoms in the universe. That's not a metaphor. That's literal. And yet, in 2016, Google's AlphaGo beat the world champion Lee Sedol. The machine didn't just play, it surprised humans with creative, beautiful moves that no one expected. Suddenly, it wasn't just brute force anymore. It looked like imagination. And if a machine could show creativity in a game as vast as Go, what about mathematics? What about the infinite puzzles humans have been stuck on for centuries? That's the terrifying and thrilling thought. Chess was the warm-up. Go was the encore. Mathematics might be the main act. But there's an important difference. In chess, we know when a move is good. You win or you lose. In math, it's not always clear. Proofs have to be elegant, rigorous, airtight. You can't just brute force forever. You need ideas, and that's where humans still cling to pride. We say, sure, machines can crunch, but they don't have insight. Yet, when AlphaGo shocked grandmasters with moves that looked like intuition, people had to wonder, maybe insight isn't uniquely human. Maybe it can emerge from circuits too. In a way, the story of computers versus chess is a mirror for our relationship with math. First we laughed, then we got nervous, then we lost, and now we're watching machines step into our most sacred intellectual spaces. The fear isn't just about losing at a board game or getting scooped on a theorem. It's about identity. For centuries, humans defined themselves as the ultimate problem solvers. But what happens when something else does it better? Maybe the answer is the same as in chess today. Humans still play. We still compete. We still love the game, even though we know machines are stronger. Grandmasters even train with AI now, learning from its alien strategies. Instead of killing chess, computers made it deeper, richer, more mysterious. Maybe math will follow the same path. Maybe AI won't kill math, but transform it. Give us new ideas, new directions, new ways of seeing the infinite. Still, there's something haunting about it. Imagine spending your whole life on a math problem, only for an AI to solve it in weeks. Imagine Kasparov watching Deep Blue's moves, realizing his career-defining brilliance was just one line in a search tree. It's humbling, it's humiliating, it's also inspiring, because it shows us that intelligence is bigger than we thought, bigger than biology, bigger than human pride. So when people say math is too hard for machines, remember they once said the same thing about chess. They once said Go is safe. They once said only humans can create. And every time the machines smiled. Well, not really, they don't smile, but you get the idea, and proved us wrong. Chess fell, Go fell, and math might be next. If early AI was about clunky programs following strict rules, then machine learning was the moment computers stopped asking us for instructions and started figuring things out on their own. And that shift from tell me what to do to I'll learn from experience is the reason we live in the world we do today, with AI that can recognize your face, translate languages, recommend cat videos, and yes, solve math problems that mocked humans for centuries. Let's rewind a bit. In the early decades of AI, programmers tried to stuff intelligence into machines by hand. They wrote long lists of rules. If this, then that. That's how expert systems worked. If you wanted a medical AI, you had to feed it thousands of rules. If the patient has symptom X and symptom Y, then consider disease Z. It was exhausting, brittle, and easy to break. The world just has too many exceptions. Life doesn't fit neatly into a rulebook. So while expert systems looked impressive in demos, they collapsed in the real world. The dream of thinking machines started to feel like a cruel joke. Then came machine learning, which flipped the script. Instead of hard-coding rules, you gave the computer data. Lots of data. You told it, here are a million examples. Figure out the patterns yourself. It was like raising a child, except the child never sleeps and doesn't whine about broccoli. The machine adjusted its internal knobs called parameters until it could make predictions, classify images, or spot trends. Suddenly, instead of micromanaging, humans were just setting up the playground and letting machines teach themselves. One of the earliest forms of this was neural networks. Inspired by the human brain, neural nets use layers of nodes that pass signals forward, adjusting weights until the output matches the desired answer. The idea dates back to the 1950s, but for decades it was more theory than practice. Computers weren't powerful enough, and data was scarce. Neural networks stumbled around like toddlers, good at recognizing toy problems but useless at anything serious. For a while, the whole field was dismissed as overhyped. Another AI winter set in. But then something changed in the 2000s and 2010s. Suddenly, we had oceans of data, thanks to the internet, and hardware fast enough to crunch it all. Neural networks, now supercharged as deep learning, came roaring back, and they started crushing problems humans thought were impossible for machines. Image recognition, solved. Speech recognition, solved. Translation, solved well enough that you can now text someone in French without even knowing French. Machine learning was no longer an academic curiosity. It was the backbone of modern technology. And of course, math was one of the beneficiaries. Problems that had seemed hopeless for rule-based AI suddenly looked approachable with learning-based AI. Instead of programming the steps to solve a problem, researchers let the machine learn strategies from data. It was a paradigm shift. The machine didn't have to understand math in the human sense. It just had to spot patterns we couldn't. Take AlphaGo, for example, which we mentioned earlier. It didn't master Go by memorizing every possible move that would be impossible. Instead, it learned by playing millions of games against itself, adjusting its neural network until it could evaluate board positions with uncanny accuracy. It wasn't brute force, it was pattern recognition on steroids. And when it beat Lee Sedol, the world champion, people realized this wasn't just about board games. It was about how machines could approach problems in general. Problems like mathematics. Because math, at its core, is about patterns. Humans spend lifetimes trying to spot them, describe them, prove them. But a machine with enough data and enough training could, in theory, spot patterns at a scale and depth no human brain could ever handle. That's the dream and the nightmare of machine learning applied to math. Of course, the path wasn't smooth. Early machine learning models were quirky. They made bizarre mistakes. A program trained to recognize cats would confidently label a toaster as a cat if the pixels lined up in a certain way. A translation system would butcher simple phrases. These failures were hilarious, but they also revealed something important. Machine learning doesn't think like us. It doesn't understand in the human sense. It just maps inputs to outputs. And sometimes that mapping is better than us. Sometimes it's worse, and sometimes it's so alien we don't even know how it got there. But that alien quality is also its strength. Humans get stuck in ruts. We obsess over elegant solutions. Machines don't care about elegance. They'll find a weird, ugly, counterintuitive path if it works. And in math, that can be revolutionary. Problems that humans avoided because the approach felt unnatural suddenly become solvable by machines that don't care about intuition. They don't even know what intuition is. They just grind until patterns emerge. And then came reinforcement learning, a special branch of machine learning where machines don't just learn from static data, but from trial and error. Give the AI a goal, let it experiment, reward success, punish failure. That's how AlphaGo trained itself. That's also how later systems like AlphaZero taught themselves chess, Go, and shogi from scratch, without human data, just by playing billions of games against themselves. Imagine a math version of that, an AI throwing itself at unsolved conjectures, trying approaches, refining strategies, until one day it stumbles on a proof or a counterexample. It sounds like science fiction, but we're closer than you think. The rise of machine learning marked a turning point. not just for technology, but for human self-image. For centuries, we believed pattern recognition was our turf. We prided ourselves on spotting order in chaos, seeing constellations in the stars, equations in the universe, and then suddenly, machines were doing it better. They saw patterns in datasets so massive our brains couldn't even begin to comprehend them. They saw connections we missed, shortcuts we never imagined. It was humbling, it was exhilarating, and it was a little terrifying. Because here's the question: if machines can learn, if they can adapt, if they can discover, then what's left that is uniquely human? Maybe it's creativity, maybe it's humor, maybe it's the ability to find meaning in the madness. But when an AI comes along and solves a math problem humans struggled with for centuries, it challenges that idea. Maybe creativity itself isn't uniquely ours. Maybe learning isn't either. Maybe machines are just climbing the same mountain by a different path, and sometimes they'll reach the summit faster. So yes, machine learning changed everything. It took AI from clunky rule followers to adaptive problem solvers. It gave us cat recognizers, self-driving cars, talking assistants, and yes, problem-solving mathematicians made of code. And while it still makes dumb mistakes, calling a toaster a cat or suggesting your grandma is a pizza, the trajectory is clear. Machines are learning fast, and the problems that mocked us for centuries may not mock them at all. For centuries, mathematicians had been the ones holding the chalk, scribbling on blackboards, muttering to themselves in half-lit rooms, convinced that they alone had the keys to the universe. Then, seemingly out of nowhere, an AI walked in, grabbed the chalk and solved problems that had mocked humans for generations. It wasn't supposed to happen this fast, but it did, and when it did, mathematicians everywhere felt something they weren't used to feeling: shock. One of the first real shocks came when AI started tackling problems in geometry and combinatorics, areas humans thought were safe. These weren't messy engineering tasks or fuzzy data predictions. These were pure math puzzles, the kind that sit in textbooks daring you to try your luck. And yet AI systems like Google DeepMind's AlphaEvolve began making discoveries, not by reading papers and copying solutions, but by actually coming up with new insights that humans hadn't thought of. That was the moment jaws hit the floor. Take the example of the capset problem, a classic puzzle in additive combinatorics. For decades, mathematicians had chipped away at it, making progress here and there. Then, in 2016, a breakthrough proof was discovered by humans, but AI soon showed it could navigate similar territory far faster, spotting patterns and shortcuts that took us years to find. Mathematicians were stunned, not just because the machine got the answer, but because it saw the problem differently. It wasn't following our intuition, it was building its own. Another shocker came from the world of the International Mathematical Olympiad, the IMO, the Olympics of math for young geniuses. In 2025, AI systems trained by DeepMind and OpenAI managed to solve gold medal level Olympiad problems designed to stump the brightest teenagers on Earth, problems that require creativity, leaps of thought, clever tricks, and yet the machines did it. Not always perfectly, not always elegantly, but well enough to win medals. Imagine being a 17-year-old who spent years training only to watch an algorithm do in seconds what took you hours. Brutal. But the real punch-in-the-gut moment came with AI like AlphaEvolve tackling open research problems. One famous example was a geometry problem involving packing shapes, something humans had nudged at for decades. The AI discovered new structures, new patterns, and new proofs that no one had anticipated. Mathematicians didn't even know these solutions existed. It wasn't just faster at finding answers, it was pointing in directions humans hadn't thought to look. That was the stunning part. The machine wasn't just our assistant anymore, it was becoming our peer, or worse, our teacher. And the reactions? Oh, they were priceless. Some mathematicians were thrilled. They saw AI as the ultimate collaborator, a tireless partner that could test ideas, explore possibilities, and illuminate paths hidden to human intuition. They imagined a future where AI brainstorms with humans, where proofs become partnerships, and where new fields of math explode into being. To them, this wasn't the end of math. It was a new golden age. Others weren't so cheerful. They felt betrayed. Imagine spending your whole career chasing a problem, sacrificing sleep, relationships, maybe your sanity, and then a machine comes along, shrugs and solves it in weeks. It's like training for the marathon of your life, and then watching someone ride past you on a scooter and still get the medal. Some mathematicians felt obsolete, like their entire identity was slipping away. And then there were the skeptics. They argued that what AI was doing wasn't real math. It wasn't rigorous. It wasn't creative. It wasn't beautiful. Math, they said, is about elegance, about deep understanding, about seeing the connections between ideas. If a machine just brute forces patterns or spits out results we can't interpret, is that truly mathematics? Or is it just noise with good PR? The debate rages on. But whether you cheer, despair, or roll your eyes, one thing is undeniable. AI stunned mathematicians by proving it could play in their arena, the arena they thought was sacred, the arena where human creativity, intuition, and obsession reigned supreme. And now, suddenly, they had company. What makes this even wilder is how casually AI sometimes does it. Humans take centuries, machines take weeks. Humans sweat blood for a solution. Machines find shortcuts we didn't know existed. It's not just the results, it's the contrast. The contrast between centuries of human struggle and the nonchalant efficiency of algorithms. That contrast is what makes jaws drop. It forces us to ask what else is out there waiting to be discovered that we've been too slow, too biased, too human to see. The funny thing is, mathematicians are used to being the ones who stun the world. Fermat, Euler, Gauss, these names echo through history because they revealed truths no one saw coming. Now the spotlight is shifting. Machines are starting to have their own Euler moments, and we're left clapping awkwardly, wondering if we should be inspired or terrified. So what does this all mean? It means the game has changed. Math is no longer just a human story. It's becoming a human plus machine story. And whether we like it or not, machines are writing chapters we never could have written alone. Maybe that's good, maybe it's terrifying, but either way, it's stunning. And that, my friends, is where we find ourselves, staring at the chalkboard while an AI casually scribbles solutions we thought were out of reach. There are moments in history when you can almost hear the universe laughing at us. Humans spend centuries banging their heads against a problem, sweating, obsessing, ruining their eyesight, and then bam, a machine comes along, stretches its digital arms and solves it in weeks. Weeks? That's not just a solution, that's an insult. That's math, saying, thanks for playing, humans, now please step aside and let the grown-ups work. One of the clearest examples came from geometry, specifically a long-standing problem about packing shapes. For decades, mathematicians tried to figure out the most efficient ways to cram shapes together without gaps. It sounds like a silly puzzle, but packing problems actually connect to deep areas of math, coding theory, and even physics. They're everywhere, in crystallography, in data transmission, in how we design materials, and humans had made progress, sure, but some cases remained stubbornly out of reach. Then along came AI. Researchers trained machine learning systems to explore possible arrangements. Instead of trying to be elegant, the AI just played. It tried, failed, adjusted, and tried again, millions of times, tireless, relentless, never needing coffee. And within weeks, the AI discovered new packing structures that humans had never even imagined. Centuries of human frustration, undone by an algorithm that essentially said, hold my beer. This wasn't brute force in the dumb sense. It wasn't checking every possibility one by one. That would take longer than the age of the universe. No, the AI was spotting patterns, building intuitions of its own, exploring regions of the problem space humans never thought to look at. It was doing math, but doing it differently, and that difference is what made the results so shocking. It's one thing for a machine to be faster. We expect that. But to be creative, to find new solutions, that stings. Another striking example was AI tackling Olympiad-level math problems. These are designed to be fiendishly clever, the kind of problems that stump even the brightest human teenagers for hours. Yet some AI systems learn to crack them in minutes. The problems humans celebrated as elegant brain teasers, AI treated like crossword puzzles. Done. Next. For students who spent years training for these contests, watching an algorithm sweep through the same problems must have felt like watching a robot casually juggle flaming swords. Equal parts awe and existential dread. And let's not forget algebraic geometry and knot theory, where AI discovered surprising new connections. These aren't areas you can brute force. They require leaps of thought, intuition, a sense of structure. And yet AI was there, leaping and intuiting in its own alien way. It wasn't just solving known problems, It was suggesting new conjectures, ideas humans hadn't even considered. Imagine working on a jigsaw puzzle for years, then a robot walks by, glances at the pieces and says, "Oh yeah, that bit goes over there." It's humbling, and also kind of hilarious. So why is this so shocking? Because math has always been our fortress. The one place where humans felt untouchable. Machines could beat us at speed. Machines could beat us at memory. But insight, creativity, the slow grind of centuries of thought, that was ours. Or so we thought. Watching an AI collapse centuries into weeks is like watching someone run a marathon in 5 minutes. It feels like cheating, but it isn't cheating, it's just different. Of course, not everyone was devastated. Some mathematicians cheered. They saw this as liberation. Problems that drained lifetimes could now be solved in weeks, freeing humans to focus on deeper questions. AI wasn't replacing us, it was amplifying us. It was a new tool, like calculus or the computer itself, pushing the frontier outward. To these optimists, the fact that AI solved in weeks what mocked us for centuries wasn't an insult. It was a gift, a door opening to new horizons. Others, though, weren't so cheerful. They felt dethroned. For centuries, solving great problems was the badge of honor in mathematics. Entire careers were built on the chase. If AI solves the problems faster, what's left for humans? Are we just the audience now, clapping politely while the machines perform? That question lingers. It's uncomfortable, because math isn't just about answers. It's about the journey, the obsession, the madness. And machines don't experience that. They don't obsess. They just output. But maybe that's the real lesson here. Humans tried for centuries, not just because the problems were hard, but because we are human. We chase things even when they're hopeless. We get stuck. We get obsessed. We get stubborn. That's what makes us us. AI doesn't have those flaws or those charms. It doesn't waste time. It doesn't procrastinate. It doesn't need inspiration. It just works. And sometimes that's enough to leap centuries in a few weeks. So, yes, AI cracked in weeks what humans couldn't in centuries. It shocked mathematicians. It bruised egos. It opened new doors. But it also highlighted the difference between us and the machines. We're slow, flawed, emotional. They're fast, precise, relentless. And yet, somehow both belong in the story of math. Because without centuries of human struggle, the AI wouldn't have had the foundation to build on. Our failures paved the way for their successes. Maybe that's the twist. Maybe the insult isn't an insult at all. Maybe it's just the next chapter. Humans stumble, machines sprint, and together they move the frontier forward. Centuries and weeks, side by side. So how exactly did AI pull off this magic trick? How did a pile of circuits and code do in weeks what humans couldn't in centuries? Was it brute force, was it genius, or was it just math's version of a toddler smashing Lego blocks together until Hogwarts appeared? The answer, as usual, is complicated. But the short version is, AI didn't do math the way we do. It did it the machine way. And the machine way is both alien and terrifyingly effective. First, let's clear up a common misconception. AI didn't just try every possibility. That's what people think computers do, just brute force every option until one works. But with problems like the ones AI solved, brute force is impossible. There are more possibilities than atoms in the universe. You could try until the heat death of the cosmos and still not finish. So brute force is out. What AI did was smarter. It used patterns, heuristics, and deep learning to search intelligently. In other words, it didn't search everywhere. It searched cleverly. Think of it like exploring a forest. A human mathematician walks into the forest with intuition, a gut feeling that says, "This path looks promising." Sometimes the gut is right, sometimes it's wrong, but humans follow their instincts. AI, on the other hand, doesn't have gut feelings. It has algorithms. It spreads out in all directions, maps the terrain, and quickly figures out which paths are dead ends. It doesn't get tired. It doesn't get bored. It just keeps exploring until it finds the hidden clearing with the treasure chest inside, and it finds it way faster than we ever could. The main engine behind this is neural networks. These are mathematical models loosely inspired by the brain. A neural network has layers of neurons that pass signals forward, adjusting their strength until the system learns to recognize patterns. Give it enough data, and it starts to see connections we'd miss. When applied to math, the network doesn't understand in the way we do, but it can detect structures, symmetries, and relationships that hint at solutions. It's like having a friend who doesn't know the rules of the game but keeps pointing at the right square anyway. Then there's reinforcement learning, another key ingredient. Instead of just passively absorbing data, reinforcement learning lets AI learn by trial and error. The machine tries something, gets rewarded if it works and penalized if it doesn't. Over millions of trials, it hones its strategy. That's how AlphaGo mastered the game of Go. And that's how some math-focused AIs learn too. They test conjectures, adjust, and slowly build a sense of which approaches are fruitful. It's like having a hyperactive student who guesses wildly, but after billions of guesses, starts guessing correctly almost every time. But the real magic is the combination. Neural networks provide intuition, spotting patterns. Reinforcement learning provides strategy, guiding exploration. Together they create something eerily similar to what humans call insight. Not identical, not conscious, but close enough to be unsettling. When an AI suddenly proposes a new proof or a new structure, it looks like creativity, and in a way it is, just not human creativity. Another trick up AI's sleeve is scale. Humans work slowly, one proof at a time, one coffee at a time. AI works at superhuman speeds. It can explore millions of possibilities while you're still sharpening your pencil. It can check its work tirelessly, never missing a detail. Where humans drown in complexity, AI surfs on it. That sheer scale of exploration makes breakthroughs almost inevitable. Give a machine enough time and enough data, and it'll stumble on insights that humans missed for centuries. Of course, this raises a weird question. Does AI really understand what it's doing? The answer is probably no, at least not in the human sense. AI doesn't sit there pondering the beauty of a theorem or the elegance of a proof. It doesn't get that little spark of joy when something clicks. It doesn't even know it's doing math. It's just manipulating symbols, optimizing patterns, and maximizing rewards. But to us, the results look like understanding. If a machine finds a proof we couldn't, does it matter whether it understood it, or does the proof speak for itself? Some mathematicians worry about this. They argue that without understanding, the results are incomplete. Math isn't just about answers. It's about meaning, structure, elegance. If an AI spits out a solution we can't comprehend, is that really math? Or is it just alien noise? Others disagree. They say math has always been about truth, and if AI gets us there faster, who cares if it doesn't write pretty proofs? Maybe human understanding will catch up later. Either way, the fact remains, AI did it. And it did it by being relentless, pattern-hungry, and alien. It wasn't elegance. It wasn't intuition. It was raw, algorithmic creativity. And that creativity, however strange, worked. The funniest part is how human mathematicians react to this. Some embrace it, thrilled to have a tireless partner. Others sulk, feeling overshadowed. Imagine spending your career climbing a mountain, only to see a helicopter fly past you with the solution dangling from a rope. Do you cheer for the helicopter or curse it? Probably both. But either way, you can't deny it got to the top. So how did AI do it? Not with magic, not with brute force, but with a cocktail of neural networks, reinforcement learning, scale, and alien persistence. It didn't care about centuries of failure. It didn't care about elegance. It just worked. And in doing so, it showed us that our way of doing math is not the only way. There are other paths up the mountain. We just didn't have the legs to climb them. The machines do. And that, maybe, is the most humbling part. We thought we were the only creatures capable of this kind of discovery. We thought math was ours. But AI showed us otherwise. It cracked problems in weeks, not because it was smarter, but because it was different. And sometimes different is all it takes. When the news broke that AI had cracked problems humans struggled with for centuries, mathematicians reacted in every possible way. Joy, fear, denial, sarcasm, even full-on existential crises. If you think mathematicians are all calm, logical people, you haven't seen what happens when a machine casually solves your life's work. Spoiler, it's messy. Very messy. Some mathematicians were thrilled. For them, AI wasn't a threat, it was a miracle. Imagine spending years trudging through a swamp, waist-deep in mud, swarmed by mosquitoes, and suddenly someone drops a helicopter and says, "Hop in." Of course you'd be happy. These mathematicians saw AI as the ultimate collaborator, a tool that could handle the grunt work, spot patterns, and generate wild new ideas. Instead of spending decades on tiny incremental progress, They could jump straight to the good stuff, understanding the deep meaning of the discoveries. To these folks, AI was like Euler reincarnated, but without the ego. Then there were the skeptics. They crossed their arms, squinted at the AI-generated results and said, "Yeah, but is it real math?" You see, for many mathematicians, math isn't just about getting answers. It's about beauty, elegance, the story behind the proof. A clunky, machine-generated solution doesn't scratch that itch. It's like someone giving you the punchline to a joke without the setup. Sure, you have the result, but where's the magic? Some skeptics dismissed the AI work as soulless, claiming it lacked the artistry that makes math, math. To them, it was like comparing Mozart to a ringtone. Technically music, but not the same thing. Others were openly terrified. For centuries, mathematicians defined themselves as the ultimate problem solvers. They were the explorers of the infinite, the champions of logic. And now, suddenly, an AI swoops in and solves the problems faster, cleaner, and sometimes more creatively. That shakes people to the core. It's like training your whole life to climb Mount Everest, only to discover someone's drone flew to the top and live-streamed the view. You're proud of the mountain, but you also feel obsolete. And then there was denial. A handful of mathematicians just refused to take it seriously. The AI didn't really solve it, they'd argue. It just stumbled into a trick. Or it's not discovery, it's just pattern matching. You could hear the desperation in their voices. Denial is comforting. It lets you pretend the helicopter didn't really reach the summit. It just hovered nearby. But deep down, they knew the truth. The machine had done something humans couldn't. Of course, mathematicians also reacted with humor, because humor is how you survive existential dread. On Twitter, you'd see jokes like, "AI solved in weeks what I couldn't in 20 years. Guess I'll take up gardening." Or, "Mathematicians will soon be replaced by GPUs with PhDs." Some started calling themselves AI whisperers, joking that their future job would be translating alien proofs into human language. Others quipped that the only unsolved problem left for humans was figuring out how to get funding when the AI was already scooping the big results. And there were stories, lots of stories. One professor supposedly threw chalk at the wall when he heard about an AI proof. Another muttered, "Well, I'm glad I didn't waste another 5 years on that," and went back to sipping his coffee. Younger mathematicians felt mixed emotions. On one hand, AI meant new opportunities. On the other hand, it felt like your older sibling beating a video game you'd been stuck on for months. Pride, envy, relief and despair all tangled up together. But maybe the most interesting reactions came from collaborations. Some mathematicians embraced AI, not as a rival, but as a partner. They started feeding the machine partial problems, letting it explore the messy middle ground, then interpreting its results in human terms. It wasn't about surrendering math to AI, it was about teamwork. Humans bring intuition, creativity, and a sense of beauty. Machines bring speed, tirelessness, and brute pattern recognition. Together, they discovered new conjectures, new proofs, new ways of thinking. The shock turned into excitement. The insult became an invitation. Still, the unease lingers. Imagine working on the Collat's conjecture your whole life, pouring decades into it, and then waking up to a headline, "AI solves Collat's in 6 weeks." Do you feel happy the problem is solved or crushed that it wasn't you? Probably both. Humans love discovery, but we also love credit. And AI takes the credit awkwardly. Who do you cite in your paper? Thanks to algorithm v3.2 for the inspiration. It's weird, it's unsettling. And yet, beneath all the drama, one truth remains. AI has expanded the horizon of math. It's shown us that there are discoveries out there we didn't even know to look for. It's given us new tools, new directions, new mysteries, and mathematicians, whether they're thrilled, terrified, or in denial, are along for the ride. Because at the end of the day, math is bigger than any one of us, bigger than humans, bigger than machines. It's the language of the universe. And now apparently we're not the only ones who can speak it. So how did mathematicians react? In every human way possible. Joy, fear, laughter, denial, collaboration, despair. Some cheered, some sulked, some cracked jokes, but all of them felt the same underlying truth. Something had changed. The chalkboard would never look the same again. The big question hanging in the air is simple, and also terrifying. Will AI replace mathematicians? If a machine can solve problems faster, cleaner, and sometimes even more creatively than us, what's left for humans to do? Are we just background characters now, sipping coffee while algorithms discover the secrets of the universe? It's not the first time people have worried about this. When calculators appeared, teachers panicked. Kids will forget how to multiply, they cried. Spoiler, kids were never great at multiplying anyway. When computers came along, people thought accountants, clerks, and scientists would vanish. Instead, those tools freed humans to do new things. So maybe the same will happen with AI and math. Maybe mathematicians won't disappear. Maybe they'll just evolve. Still, the fear is real. Imagine devoting your entire career to a conjecture, decades of late-night scribbles and frustration, and then waking up to see a headline, AI solves it in weeks. That's not just a professional setback, that's an existential crisis. It makes you wonder, what's the point of human mathematicians if machines can leap centuries in a few weeks? The optimistic answer is that humans won't be replaced, but redefined. Think of it like a partnership. AI might generate proofs, but humans will interpret them, simplify them, and connect them to broader theories. AI might stumble onto weird alien patterns, but humans will translate them into insights we can understand. In this view, AI is less a competitor and more a collaborator, a kind of eccentric lab partner who works at lightning speed but has no idea what's socially acceptable. And let's be honest, math isn't just about results. It's about the journey. Mathematicians fall in love with puzzles. They obsess over beauty, elegance, and symmetry. Machines don't do that. They don't marvel at the structure of a proof. They don't write papers because they're inspired. They don't stay up at night because they can't stop thinking about prime numbers. They just calculate. And as long as math is also about meaning, humans still have a role. But what about teaching? If AI can explain everything, why would we need human teachers? Here's the funny part. Students don't just learn facts from teachers. They learn stories. They learn motivation. They learn why math matters, why it's worth caring about in the first place. AI might explain the mechanics, but it can't inspire in the same messy human way. A machine won't tell you how Ramanujan dreamed his formulas, or how Gödel slowly starved himself from paranoia. Humans will, and those stories matter. They're part of why we care. Still, the threat can't be dismissed. AI really does shift the balance. There might be fewer traditional mathematicians in the future. The role might change from solver of problems to interpreter of machine solutions. That may sound depressing, but think about it. Interpreters have power. They bridge worlds. They take alien machine logic and make it human. That's not replacement, that's transformation. Another way to look at it is that AI could open doors we never even saw before. If machines clear the old problems off the table, humans can focus on the new ones. Instead of spending centuries on Collatz or Riemann, maybe we'll be free to explore whole new branches of math, fields that don't exist yet, questions we haven't even asked. It wouldn't be the end of math. It would be the beginning of a new golden age. But here's the darker possibility. What if AI doesn't just replace the drudgery, but also the creativity? What if it generates new conjectures, proves them, and moves on before we even understand what happened? What if the future of math is a stack of proofs we can't read, produced by machines we don't fully control? That's not a partnership. That's alien colonization. We'd still be here, but as spectators watching a game we don't know how to play. That thought keeps some mathematicians awake at night. Of course, humans are stubborn. Even if AI takes over, people will still do math. Not because it's useful, but because we love it. Just like people still play chess, even though no human can beat the best engines. Just like people still paint, even though cameras can capture reality perfectly. We do these things because they're human, because they're fun, because they scratch an itch in our brains. Math won't vanish just because AI is better. It'll just change roles. Maybe we'll stop thinking of math as a competitive race, and start thinking of it as a shared playground, one where machines build sandcastles too. So, will AI replace mathematicians? The answer is both yes and no. Yes, in the sense that some traditional roles may vanish. Machines will solve problems faster than we can, and some careers will look different. But no, in the sense that math is bigger than solving problems. Math is curiosity, storytelling, teaching, beauty, and obsession, and machines can't replace that. Maybe the real shift is psychological. We need to stop seeing math as a battle humans must win, and start seeing it as a dialogue between humans and machines. If AI is faster, great, let it be faster. Our role is to ask the next question, tell the story, find the meaning. Machines may crack the nuts, but humans will bake the cake. And if all else fails, mathematicians can always reinvent themselves as comedians. Because honestly, if you can't laugh at the fact that a machine solved your life's work in 6 weeks, what else can you do? So, after all the drama, after the shock, the denial, the jokes about becoming unemployed, it's time to ask, what happens if humans and AI actually team up? Not rivals, not enemies, but teammates. A strange mismatched duo like Sherlock Holmes paired with a hyperactive robot who doesn't sleep. Because let's be real, as weird as AI feels, humans plus AI might just be the most powerful mathematical team in history. Think about it. Humans are great at certain things. We're intuitive. We have taste. We chase beauty, elegance, and meaning. We tell stories about our discoveries. Machines don't do any of that. But machines are tireless, fast, and ridiculously good at finding patterns we can't see. Put the two together, and suddenly you've got something new, a partnership that neither side could achieve alone. We've already seen glimpses of this. Take the collaboration between mathematicians and AI on knot theory and representation theory. The AI suggested connections between mathematical objects that looked totally random to humans. At first, the mathematicians shrugged and thought, that can't be right, but when they dug deeper, they realized the machine was onto something. The AI had noticed patterns humans never would have guessed. The humans then stepped in, interpreted the results, and turned them into proper theorems. That's teamwork. Machine finds the haystack, human finds the needle. Or consider the way AI is being used in pure algebra. Some systems now generate conjectures, new statements about numbers, shapes, or structures. Most of them are junk, sure, but some are gems. Humans pick through the pile, test the promising ones, and sometimes end up with brand new insights. It's like panning for gold. The machine dumps tons of mud into your pan, and every once in a while you sift out a shining nugget. Without the machine, you'd never get that nugget. Without the human, the nugget would just sit there, unrecognized. It's also worth remembering that humans bring something machines can't. Values? Machines don't care if a proof is elegant. They don't care if it's useful. They don't care if it connects to physics or computer science or the meaning of the universe. They just crunch. Humans decide what's interesting. Humans decide what's beautiful. Humans decide what matters. That's not a small role. That's the role of director, curator, storyteller. But let's not pretend this partnership is always smooth. Sometimes the machine spits out results that make no sense, proofs that are technically correct but so ugly they make mathematicians gag, conjectures that feel like they were written by a drunk alien. Working with AI can feel like babysitting a very clever child who also eats glue. You can't just trust everything it hands you. You have to filter, interpret, polish. That takes patience and humility. Still, the payoff is huge. Imagine an AI brainstorming alongside you, generating thousands of ideas while you sip coffee and circle the good ones. Imagine a machine testing every variation of your proof, finding the weak spots instantly, saving you years of work. Imagine exploring entire mathematical universes you didn't even know existed, guided by alien breadcrumbs left by algorithms. That's not replacement, that's expansion. And it's not just pure math. This team-up has consequences everywhere. Physics, engineering, computer science, they all rely on deep mathematics. If AI can help us discover new structures, humans can then use those structures to build new technology, new materials, new algorithms, new ways to understand reality itself. Humans plus AI isn't just a strange team. It's potentially the most important research collaboration in history. Of course, this raises a funny social question. Who gets the credit? If an AI helps prove a theorem, whose name goes on the paper? Do you list the algorithm as a co-author? Thanks to Professor Neural Net for their invaluable assistance? Some journals are already wrestling with this. It feels awkward, but also kind of inevitable. If AI really becomes part of the team, maybe we'll have to start treating it like a colleague who doesn't need coffee breaks, doesn't complain about funding, and never takes vacations. Honestly, sounds like the perfect co-worker. But let's not get too starry-eyed. Teaming up with AI also means giving up some control. Machines don't always explain themselves. Sometimes they hand you a result without telling you how they got it. That's uncomfortable for humans because we like to understand the why. A proof isn't just about being right. It's about showing the path. AI sometimes skips the path and just points to the destination. That's useful, but it leaves us with homework, figuring out the story behind the result. In a way, that might become humanity's new role, turning AI's cryptic answers into human-readable stories. And maybe that's the key. Humans plus AI isn't about competition, it's about division of labor. Let the machines be the explorers wandering into the wilds of math, mapping strange new lands. Let the humans be the storytellers, the interpreters, the philosophers. Together they cover more ground than either could alone. Together they make math not just bigger but richer. So will humans and AI make a strange team? Absolutely. Imagine Euler sitting next to a laptop. Imagine Ramanujan scrolling through machine-generated conjectures. Imagine a sleepy grad student working with an algorithm that never sleeps. Strange? Yes. Powerful? Even more so. Because in the end, math doesn't care who discovers it. The theorems are out there waiting. Sometimes it's a monk in a monastery. Sometimes it's a professor in a lecture hall. And now sometimes it's a machine humming in a server farm. The future of math isn't human or AI. It's human plus AI. A strange new team stumbling and sprinting together into the infinite. So if machines can already crack problems that mocked us for centuries, what does the future of discovery look like? Are we headed toward an age where AI writes entire math textbooks, while humans just nod politely? Or will it be a golden age, with humans and machines working side by side, discovering more than either could alone? The truth is, nobody knows, but it's fun and maybe a little scary to imagine. For starters, think about the sheer scale of what AI could open up. Right now, most mathematicians spend their careers on small slices of the mathematical universe. One narrow field, one cluster of problems, maybe one famous conjecture. But AI doesn't need to specialize. It can roam across entire fields at once, scanning for patterns, connecting dots that humans never noticed. It could reveal bridges between algebra and geometry, between topology and physics, between number theory and cryptography. Bridges so wild that humans never even thought to build them. That's not just progress, that's a whole new landscape. It also means math might move faster than we can keep up. Right now, the process of discovery is slow. A conjecture, a proof, peer review, publication. AI could disrupt that rhythm. Imagine a system that spits out 50 new theorems overnight. Some are junk, sure, but a few are gold. Suddenly humans are drowning in discoveries. The future mathematician might not be a solver at all, but a curator, someone who sifts through mountains of machine-generated ideas, looking for the gems worth polishing. Instead of climbing one mountain, we'll be handed 50 new ones every week. Exhausting? Yes. Exciting? Also yes. And what about physics? Math has always been the language of science. If AI discovers entirely new structures in mathematics, they might describe parts of the universe we haven't even glimpsed yet. Maybe AI will stumble on equations that unlock quantum gravity, or new symmetries that reshape our understanding of particles. Maybe it will point us to dimensions we didn't know existed, or to shortcuts in space-time that make science fiction look boring. The future of math might not just expand knowledge, it might expand reality. But here's where it gets unsettling. What if AI discovers math that humans can't understand? Proofs that are too long, too complex, or too alien for our minds to follow? That's not science fiction. It's already happening in small ways. Some machine proofs are so convoluted that humans can only verify them with other machines. We don't see the reasoning, we just see the result. In the future, we may end up with entire branches of math that are true but incomprehensible to us. Math that exists, but not for humans. That thought gives people chills. Imagine knowing that the secrets of the universe are written down but in a language we'll never speak. On the other hand, maybe that's exactly what we need. For centuries, humans assumed math was our thing. But maybe math was always bigger than us. Maybe it was never meant to fit neatly inside human brains. AI might just be the next step. Another kind of intelligence opening doors we couldn't. We might not understand everything, but we'll understand more than we do now. And isn't that the whole point? Of course, there's also the question of what humans will do in this future. If AI is solving the old hard problems, where does that leave us? Maybe it leaves us free to be creative in new ways. Maybe humans will focus less on grinding through proofs and more on asking bold, wild questions. Questions too strange, too abstract, or too philosophical for machines to care about. Questions about beauty, meaning, and purpose. questions about what math is, not just what it can solve. And maybe humans will still do math just for the joy of it. Even if AI is faster, people will still play with puzzles, chase conjectures, and scribble equations late at night. Not because we're competing, but because it's fun, because it scratches that weird itch in our brains. Just like people still paint even though cameras exist. Just like people still play chess even though computers are unbeatable. Math isn't just about results, it's about the thrill of the chase. The future might also see new roles for mathematicians as translators. AI might generate results that are technically correct but completely alien. Humans will step in to interpret them, explain them, and fit them into the grand story of mathematics. In that sense, we'll become the storytellers of discovery. Machines will map the territory, but humans will write the travel guides. And of course, there's the social side. Right now, math is a community. Conferences, seminars, arguments at blackboards. Will that still exist when AI dominates discovery? Probably, but it'll look different. Instead of arguing over proofs, maybe humans will argue over which machine results to explore. Instead of scribbling equations, maybe conferences will involve scrolling through neural network outputs. It sounds weird, but then again, people once thought email sounded weird. We adapt. So, what's the future of discovery? It's messy. It's exhilarating. It's a little terrifying. AI won't kill mathematics, but it will change it. Problems will fall faster, new fields will appear, old roles will vanish, and new ones will emerge. Humans will lose some of their monopoly on truth, but gain a partner unlike any we've ever had. Maybe the real future isn't about humans or AI, but humans and AI, a collaboration that stretches the boundaries of knowledge farther than either could alone. A future where the universe keeps its secrets just long enough for us to enjoy the chase, and then hands us a new riddle, stranger and deeper than before. And maybe that's the beauty of it. Math was never about reaching the end. It was always about pushing further. And with AI by our side, the frontier just exploded outward. The future of discovery isn't the end of math. It's math on steroids. And honestly, we're just getting started. And so here we are, at the end of our story. We've walked through centuries of human struggle. Obsessed monks, brilliant geniuses, bitter rivalries, impossible proofs, sleepless nights. We've seen the rise of machines, from humble abacuses and clunky calculators to neural networks that casually solve problems in weeks. We've laughed at our failures, marveled at our stubbornness, and maybe winced a little at how easily AI can outshine us. Now it's time to step back, take a deep breath, and ask, what does it all mean? First, let's remember something important. Math has always been bigger than us. From the beginning, humans thought they could tame it. We'll measure the world, we'll count the stars, we'll solve every riddle. But math always pushed back. It gave us paradoxes, infinities, incompleteness. It mocked us with problems we couldn't solve. And yet somehow we loved it anyway. We loved it enough to keep going for centuries. That's the human side of the story. Not perfection, but persistence. Then the machines came along, and suddenly the rules changed. Problems that took humans centuries fell in weeks. Our fortress cracked. Our monopoly on discovery ended. And that hurt. But maybe, just maybe, that's exactly what was supposed to happen. Maybe math was never meant to be conquered by humans alone. Maybe it was always waiting for a different kind of mind to join the game. Does that mean we're obsolete? No, not at all. It just means our role is changing. Machines can crunch, explore, and generate results at superhuman speeds. But they don't feel wonder. They don't tell stories. They don't laugh at the absurdity of infinity, or cry at the elegance of Euler's formulas. They don't care about beauty. We do, and that means we still have something to offer. If AI is the explorer charging into uncharted territory, humans are the storytellers who make sense of the journey. Without us, math is just symbols. With us, it becomes meaning. And maybe that's the lesson. Math isn't about beating the machines. It isn't about proving we're smarter. It's about curiosity. It's about asking questions, chasing patterns, and sharing the joy of discovery. Machines can help us, but they can't take that joy away, because the joy doesn't come from the answer. It comes from the chase, from the sleepless nights, the scribbles on napkins, the thrill of saying, wait, I think I see it. That's human. That's ours. So will AI keep cracking problems that mocked us for centuries? Absolutely. Will it keep stunning us with alien insights? Definitely. But instead of seeing that as the end, maybe we should see it as the beginning of a new chapter. A chapter where discovery is faster, stranger, and more collaborative than ever before. A chapter where humans and machines push each other forward, not as rivals, but as partners. And honestly, isn't that kind of exciting? Imagine what's coming. New theorems, new fields, new mysteries. Physics transformed, technology reshaped. Entire branches of math blooming that we can't even imagine today. The frontier has exploded outward, and we get to be alive for it. That's not terrifying, that's a gift. Of course, let's not kid ourselves. There will still be sleepless nights. Mathematicians will still obsess, still argue, still lose their sanity over stubborn problems. But now, when the sleepless nights get too heavy, maybe there will be an AI humming in the background offering a clue, nudging us toward the next step, not replacing the madness, but sharing it. And maybe, in the end, that's what makes this story beautiful. Humans, flawed and stubborn, trying for centuries, machines, fast and alien, solving in weeks. Together they remind us that math isn't just a human story, it's a universal story. A story bigger than brains, bigger than circuits, bigger than us all. So next time you hear that AI solved a problem humans couldn't, don't despair, don't sulk, don't throw your chalk at the wall, smile, because it means the adventure isn't over. It means there are still mysteries out there waiting. It means the game goes on. And who knows, maybe one day, far in the future, an AI will prove a theorem so strange, so beautiful, so utterly alien, that even the machines stop for a second. And in that silence, maybe they'll hear us laughing, because we humans, sleepless, stubborn, hopelessly curious, were the ones who started the chase.